Restoring old machines creates another problem: cleaning. For old grease and metal residue, I still prefer oil and diesel over most commercial cleaners, but once the original pump failed, the project slowly turned into designing a diesel-resistant peristaltic pump instead. At this point, the south bend was completely disassembled. The electrical system was removed, the base was empty, and components were spread everywhere around the workshop. Every part was covered in decades of oil, oxidized grease, dust, and metal residue. Before rebuilding anything, I wanted every mechanical surface properly cleaned and inspected, not only to make the machine look better, but to actually understand the condition of every single part. The washer itself was intentionally simple. I recovered some steel from a local scrapyard, welded a small metal basket, and fitted it inside a cheap plastic container resistant to diesel and oil. For the fluid system, I reused some fuel tubing, machine coolant hose components, and an old RC pump I already had. The pump was the only part I thought could create problems. And it did. Finding a small pump resistant to oil and diesel turned out to be surprisingly difficult. Most pumps were either too large, too cheap, or simply not designed for hydrocarbons. But there's one design makers have used forever: the peristaltic pump. The idea behind a peristaltic pump is surprisingly simple. And since the fluid only touches the tube, the real challenge becomes finding the right material. One of the most common and easily available solutions was Tygon tubing, used for chainsaws and small engines. That was it, so I decided to build my own. I wanted something simple, easy to reproduce, and easy to modify if needed. The first version was built almost entirely from standard parts: 608 bearings, a small geared motor, Tygon tubing, and a quickly printed PETG-HF body and rotor. I also embedded a nut directly into the rotor to better lock it onto the motor shaft. The opposite bearing support was designed to help balance side load while compressing the tube. And the bearing seats inside the body and front cap helped keep the rotor aligned during operation. Not sure if any of this actually helped mechanically, but it made sense in my head. A few hours later, the first prototype was ready for testing. The first test looked promising, until I realized it wasn't pumping anything. Then I lifted the fluid reservoir and suddenly it started pumping. Good flow, surprisingly smooth. But there was still a problem. Air could still pass through the tube, which meant the compression wasn't enough. I disassembled the pump, thinking it was a tolerance issue, but the cheap bearings had already developed noticeable play. I went to a local bearing supplier and replaced them with proper industrial ones. So I went back to CAD, printed a second version with some improvements, and rebuilt the entire pump. This time, the tube compression was noticeably better, the rotor felt more stable, and the flow immediately improved. Whoa. And after the second test, the pump started behaving like an actual tool. Finally, I could finish assembling the washer and start cleaning the south bend parts. After about half an hour of continuous use, the motor was getting warmer than I liked, so I added 2 small cooling fans. Problem solved. The files are available on GitHub and Onshape if you want to build or improve your own version. See you soon.